Okay, we are quite a few people now. And therefore, I would say, let's start. I hope everyone can hear what I'm saying, and I hope everyone can see the presentation. Today's topic would be the magnetic suspension balance. Before we go through this presentation, I want to introduce myself. My name is Sebastian Seibt. I'm the head of laboratory here at Linzheis, Germany. I'm a chemist. I have a chemical background, and I'm doing mainly classical thermal analysis here at Linzheis, which means DSC measurements, so calorimetric measurements, thermogravimetry, dilatometry for thermal expansion. And yeah, as said, I'm responsible for contract testing, customization of instruments, training sessions, and so on. I started here in 2013, and since then I'm working here in the lab in our headquarters in Germany. For those who do not yet know our company, Linzheis is a German family-owned company. We are mid-size, around 100 employees. We are located, or our main facility is located here in Selb in Northeast Bavaria, where we manufacture our instruments. Besides that, we have a place in the US as well as China and India, where we do service and repair, where we do customer trainings, and where we can also do some measurements. In all the other countries, we are more or less represented by distributors, by local distributors who represent us since many, many years. So you can be sure that all over the globe, wherever you are, there is a distributor or at least a Linzheis employee who can help you and guide you through our products in case you have questions or you have a request or you need some technical support. Our family, our owner family is nowadays Mr. Klaus Linzheis. You can see him on the middle picture in the upper line here. So he's our owner and CEO, and his two sons, Florian Linzheis and Dr. Vincent Linzheis, are the third generation who are responsible for the daily business, doing research and development, marketing, and daily business, and so on. The founder of our company, Dr. Maximilian Linzheis, founded the company in the 1950s and passed away in the 1990s. And as said, we are third generation family owned. On the lower pictures, you see an inside view in one of our dilatometer labs here in Germany, as well as one of our earliest products, an analog data logger, which we manufactured at the very beginning, but with the PC that was abandoned. And therefore, we are now focusing on thermal analysis only. Our product range, for those who do not yet know that, is of course the so-called classical thermal analysis, which you can see in the upper line. That means we do differential scanning calorimetry in a broad temperature range from -200 centigrades up to 2400. We do thermogravimetric measurements. We do the combination of both. So that combined TG and DC would be called STA, simultaneous thermal analyzer. Again, in a temperature range from -200 centigrades, roughly up to 2400, which is the classic thermal analysis. Besides that, of course, a lot of dilatometry for thermal expansion, shrinkage, sinter studies, kinetics of sintering. There we also go from liquid nitrogen, liquid helium temperatures even up to graphite heaters up to 2800. And a special form of dilatometry would be thermomechanical analysis, where you can do bending experiments, E-modulus determination, and so on. So as said, that's the complete range of thermal analysis. And the thermogravimetry is highlighted a little bit because today's topic, the magnetic suspension balance, would belong into that field. Then we do thermal conductivity testing in many ways. That means we have laser flash techniques, we have guarded hot plates, we have wire techniques, hot wire techniques. We have the so-called transinterface material tester, which is a special form of a non-guarded plate reader. And we also transfer this into thin film analysis, which means we do thermoelectric, thermal conductivity, electrical conductivity on thin films and layers, also as coatings, where we focused a little bit in the past years, or in the recent past years. And we also do bulk sample thermoelectrics, which means Hall effect devices, Seebeck effect devices, determining of these effects under temperature, under magnetic field, and so on. And this is a little bit where we went in the past years regarding microchips, computing, and stuff like that, semiconductor analysis. That's what we recently did. And what we also do is a lot of customization. That means all these techniques can also be performed at ultra high temperatures, which means at temperature ranges where a resistance heater is already at its limit. Speaking about 2000 centigrades and higher, we do pressurized systems, so we can operate most of our instruments under pressure. So therefore, we are able to do sorption studies, catalytic reactions, and so on. So that's basically the complete range of thermal analysis and everything that has to do with that. So that just for those who didn't know that, that's what we basically stand for. And now coming back finally, today's topic is a very special form of thermogravimetric measurement, the so-called magnetic suspension balance. So therefore, I will enlarge our range or our product portfolio of thermobalances. There you can see we have the so-called TGA PT1000. We have, which is the basic instrument with an integrated furnace that goes up to 1000 centigrades. And it is expanded to the TGA PT1600 platform. It's an instrument with a modular furnace where you can go up to 2400 centigrades by exchanging the standard furnace. The standard furnace is up to 1600. That's why it's called PT1600. And these two instruments are the typical tabletop thermobalances where you can measure thermal decomposition of any sample. You can evacuate it, you can flush it with any gas, measure under gas atmosphere, gas flow, whatever. And then we have the pressurized systems. You can see in the lower line, the SDA HP1 and 2, which is floor mounted for simulating reactor conditions, high pressure analysis up to 150 bars in the temperature range up to 1600. And if you decide to go up to 1000 only, we have the HP3 system. It's a tabletop pressurized system. And as I mentioned, all these instruments allow the use of many gases, but from time to time, you have the case that the customer has an application that needs and requires very corrosive gases, maybe even toxic gases, or the sample decomposes in something very corrosive, very toxic. It releases fluorine gases, halogen gas. It may release some sulfur, some phosphate, and so on, which could affect the balance and also is not good for the environment. And for that purpose, there's a special balance, the so-called magnetic suspension balance, the so-called MSB, which is a special shape of and a special type of balance where you have a sample reaction chamber that's enclosed. There is no contact, no physical contact to the balance. It's an enclosed atmosphere, and that's why it's something very special. So what does it mean? As I already said, MSB stands for magnetic suspension balance. So it's a classic device for thermogravimetric measurement, however, with a contactless load transmission between sample and balance. That means you have a closed reaction chamber. As said, you can measure corrosive atmospheres. You can measure even toxic and reactive samples, and there's a minimum risk for system and operator. In detail, I can show you a comparison, a schematic drawing of a classical conventional thermobalance you see on this slide. On the right side, this is the scheme of our SDA PT1600 system. I will shortly explain that. So usually you have the housing. This is the unit down here. In there, you have a vacuum-tight balance block containing your microbalance. This microbalance is holding this yellow sample rod that goes directly into the furnace. So on top of the yellow rod, you measure your sample. Maybe even you have a DSC rod, and you can also measure, of course, TGDSC here. Sample is heated. The sample sees from this gas inlets. Usually it's mass flow controlled. So you see a gas inlet, you see a gas path, you see a gas flow passing the sample. And usually you have a purge gas purging your balance chamber down here. The purge gas rises up here, goes out at the flange. The sample gas goes into the tube, is released at the top. And therefore you have almost no intermixing, but there is a risk of mixing the gases directly at the flange where the one chamber is connected with the other chamber. And there is a physical connection needed because this rod has to physically be attached to the balance unit. On the scheme in the middle, you see the concept. In case of a corrosive gas, maybe you have a corrosive gas around the sample is connected to the balance directly, the balance is flushed by inert gas, and somewhere in between you have a mix-up between inert gas and corrosive gas. I'm sorry, this is the other way around than it's shown here, but this is just a schematic drawing. So in the conventional setup, there is a risk of intermixing here. There is a certain risk of corrosive gas going into the sample chamber. It's not really high risk if it's purged properly. Usually nothing should happen, but there is still a risk. and the balance could corrode, the balance could be affected. So it's not really completely protected. The gas flow of inlet gas, the protective gas, may cause an influence on the TG signal. It may cause turbulence, convection, whatever. And therefore, you have still a residual risk that there's intermixing, that there's something corrosive and toxic attaching or reaching a sample, reaching a balance, sorry, somehow. In contrast, the magnetic suspension balance solves this problem by having a physically closed chamber. As I told you, on the right side, you see a schematic drawing of the magnetic suspension balance. It has a head containing the balance unit, which is hidden in this black gray block here. And then you have this little red parts, which is a holding and a floating magnet. So on the top side, you have usually a holding magnet, which is an electric magnet with a controlled force. On the lower part, you have a floating magnet, and they are coupled via magnetic field. And in between, the chamber of the sample is closed. So you have a floating magnet. You see it on the sheen in the middle in a, I would call it hot environment, holding a sample, so-called sample holder with the sample at the end in the reaction chamber. And that can be flushed with corrosive gas or anything. And the sample chamber is not affecting your balance unit itself by coupling it with this magnetic field up here. Again, it can be pressurized. You have an enclosed chamber. You have a sample holder, which is the green bucket you can see down here. You can apply any atmosphere, any pressure, any temperature range. And the big advantage is you have now an enclosed chamber. As said, this makes the balance is protected from high pressure, high temperatures, aggressive gases. Even for pressurized experiments, you do not have to pressurize your balance unit. So the effect of pressure on the balance signal is quite low. The purge gas is not needed anymore, and the disadvantage of using purge gas is also eliminated, which makes it a quite comfortable setup. The function in detail, how it really works, is shown on the slide. On the picture in the middle, you see a real high pressure magnetic suspension balance setup. So this is the floor mounted high pressure system if you use in a magnetic suspension balance. On the top, this part here on top is the balance unit where the balance is placed. As said, this doesn't see any purge gas. There's no need for it. It's just a balance at ambient conditions. And then it goes into this little tube. At the end of the tube, you have the levitation, so-called levitation coupling with a holding magnet, with an electric magnet over here. In the lower part, you have the reaction chamber containing the furnace, of course, that can be pressurized, holding your sample. On the right sheen, you see there is a holding magnet, and then there is this floating magnet part. There is the enclosed border of the chamber. And then there's something you should know. This floating magnet is connected to a rod. In the middle of the rod, there is a sensor array that has a core for positioning detection, and then you have sensors that detect this core for the exact positioning. If the positioning of the complete part is out of range or out of order, there is an automatic controller who controls this by PID and enforces the electric magnet or lowers the voltage of the electric magnet to keep this part in position all the time. Because if you get out of position, the magnetic force will change, and therefore it could fall down or could be attracted to the magnet too much. Down here, at the lower end of the holding part, there is a mechanical coupling to a sample holder, and the sample holder contains a kind of crucible, kind of bucket that contains the sample. This sample down here can be easily reached by opening the furnace. I will show you on the next slides. And the whole upper part, the displacement sensors, the holding magnet, and so on, they are all hidden by the instrument, which are usually not accessed by the customer directly. So this is how it functions and how it looks like. In detail, as said, the holding magnet and the suspending magnet, they have a constant magnetic force in between, and they keep the distance always constant. Out of the position transducer down here, the distance between holding magnet and suspending magnet is kept constant. The force between them is kept constant all the time. That means the positioning of the sample holding rod, the elevated part here, is also kept constant. And that's important because you want to monitor the sample weight change. So therefore, the complete part as a whole thing should pull or push at the balance over here. So therefore, the magnetic coupling should be constant and kept constant, which is the key part you have to be able to control, which is the key part you have to really precisely be able to manufacture if you want to set up such a system, which makes it a little bit, more or less difficult. The reason for this displacement transducer and why we have to use it and why we have to set it up very careful is the following. So this graphic just explains there's a range where there's a balance between the magnetic forces. So the electric magnet and the floating magnet, they have attraction, they see attraction to each other. And if they are in the right distance, it will be kept at the same distance all the time. If you lower this distance, the attractive force would be increasing. So if you lower the distance, the attraction force increases and the floated magnet would be pulled up and finally touch the chamber hull or the end of the chamber. Therefore, you have to lower the magnetic force of the electric magnet. If the force gets too weak, however, the elevated part in your balance will just fall down, and therefore you have to increase the voltage of the electric magnet. And that's why you have to precisely control the force by PID so that the coupling is kept constant. The whole regulation circle and the whole setup will cause a little bit noise on the signal, and that's also the reason why the resolution of a magnetic suspension balance is a little bit worse than of a classical thermobalance. However, you gain or you win the advantage that you can use corrosive atmospheres in an encapsulated chamber. And that's why it's very important to have a good magnetic coupling. I promised to show you how to access the sample, how the whole thing looks like if the customer or from the customer's perspective. That's the whole unit. That's the not pressurized version. The balance unit is hidden in this upper part. There is this tube with the floating magnet inside and the sample holder inside. And if the furnace, in this picture, the furnace was just removed. With an open furnace, you see this little crucible hanging there. If you magnified it on the middle picture, you see down here, there's a little hook containing this little sample holder or sample container, or call it crucible, whatever I call it, or sometimes I call it bucket. This is what the customer sees. So if he opens the furnace is lowered, and this is what he accesses. And then you can put in your sample, you hang it there, you close the furnace, and everything else is done automatically by software. That's quite easy to handle and quite easy to operate. As said, the resolution of the complete thing is a little bit worse than with a classical thermobalance. However, you gain the possibility to measure corrosive atmospheres. We as company, we offer two models, and what you need to know is we have a standard version, a standard model that is the one without pressurized chamber, which is made for a temperature range up to around roughly 900 centigrades, and it can run in vacuum up to 1.3 bar pressure inside of the furnace with a standard sample weight of 10 gram, which is no matter which version you have, 10 gram or 10 grams is the sample amount you usually can measure with that kind of instrument, with a resolution of 1 microgram. It's possible to couple mass spec, FTIR, whatever to the gas outlet. I will talk about this later. And it's mainly made for corrosive atmospheres. The standard version is made out of a glass chamber, so it's really resistant to almost anything besides hydrofluoric acid, which is a critical part, but anything else could be measured. And then we have a high pressure version, which is made of a metal chamber mainly, that goes from -196, so from liquid nitrogen up to 2400 centigrades. It can operate now up to 150 bars. So it depends a little bit on the temperature range, what's the maximum possible pressure. It's the same balance unit in general, so the same sample weight, the same resolution. Again, the resolution depends a little bit on the pressure and temperature range, so it may be a little bit worse depending on the maximum setup you have. As said, we customize our instruments pretty much, and this is a very customized instrument at all. So therefore, for the high-end version, it depends a little bit on the exact configuration. However, if you have the pressurized version, the metal version, the corrosion resistance is a little bit lower than with the glass version. However, you have higher pressure and temperature range in that case. And what I also need to mention, I told you about the setup that we have an attraction force between the holding and the floating magnet. And I know there's only one competitor out on the market doing the same stuff. In their case, they do the other way around. They do not attract, but they push the magnets from each other while we are pulling our magnets in our setup. That's the main difference between us and the other instrument on the market, but the rest is more or less the same. It results in a more or less similar instrument. I just mentioned it shortly. I will go into more detail now. So there are some options you can have with the instrument. So of course you can run in vacuum. Therefore we offer vacuum pumps up to a rotary pump and high vacuum pumps, turbomolecular pumps going down to 10-5 or 10-6 millibars. You can add water vapor or any evaporators for liquids being injected as a vapor. That can be hydrocarbons, that can be alcohols, solvents, whatever. It can be water vapor, it can be, I don't know, whatever evaporates within a certain temperature range. Usually we do that by HPLC pump evaporators that are directly attached to the sample chamber. So that's possible with our classical pressurized balances as well as the magnetic suspension balance. And then we have individual gas dosing systems that also are optional and customizable. So we can add any kind of gas control for that many sample gases that you need. In the middle of the picture, you see a typical evaporator with a couple of gas channels. And depending on the exact customer application, we usually offer to add gas control for multiple gases, depending on what he needs, how many they need, and what exactly pressure range they need. And therefore, we can customize that pretty much. So the gas coupling system is almost, for any instrument, it's almost of big interest. And of course, we offer outgassing analyzers, so we can couple the gas outlet with mass spectrometers, FTIRs, as well as GCMS systems to characterize what exactly comes out of the instrument, if your sample shows reaction, if your sample decomposes, and so on. And that's all possible to buy as an add-on, and it can be easily added to the magnetic suspension balance as well as it could to a classical standard thermobalance. A last final comparison with the classical setup. In the classical setup, as said, the main difference is you can run inert atmospheres, you can run hydrogen. However, if you want to run reactive atmospheres, hydrogen, ammonia, catalysts, and so on, the complete system needs a special setup. It needs sealings, it needs feed-throughs that are special, and you need to modify it. While the magnetic suspension balance can measure corrosive atmospheres as it is, additionally to anything else. For the classical balance, as said, they are also available as a combined TG-DSC, so as an STA instrument, while the magnetic suspension balance can do TG mode only. There is an option for a calculated DSC by adding in a DSC-like sensor. However, that's not a real DSC. It's a rough estimation of a DSC, to be fair. The classical balance can measure pressurized experiments. However, you need to modify them. You need a separate model. And the magnetic suspension balance, if you buy the steel version, you can already pressurize it. It does not require that much modification. And the application is the main difference. While the classical thermobalance has applications like co-gasification, decomposition, mainly some catalytic reactions, the magnetic suspension balance can be used for applications like a plug flow. That means like an application where you have all your sampling gas going through the sample by using a mesh type sample holder and bringing in the gas from the bottom side to the top side of the sample tube. So therefore, you can guarantee that your gas has to pass your sample. You can do applications like sorption studies. Due to it has a very small volume, so due to its small volume, and due to the fact that your sample chamber is independent from your balance unit, the pressure does not that much affect the signal. So you do not need to do a barometric TARA or something like that, or barometric calibration. You can measure sorption with a much better quality than a classical standard balance could do. And that's the main difference in comparison with the standard models. As said, these plug flow application, I will show you an example later. It's really, mentionable and very special for the magnetic suspension balance. Again, this picture just shows the setup. If you do something with water vapor, that's an example of an existing system. That's how it looks like. If you have a plug flow, if you have a gas outlet or gas inlet from the top side to the bottom side, it can be also the other way around from the bottom side to the top side. So you have gas inlet and outlet on top and bottom of the chamber. You have a water evaporator at the side coming from here. So on the real picture, it's this part. It can bring in water steam. It can bring in even other gases. you have the furnace chamber down here, you have the balance load unit on top. So that's how it would look like in this kind of setup. And I already have to mention there's another special setup, which is the modification if you want to attach it to a glove box. We sometimes had customers in the past who are doing really corrosive stuff, who are doing really dangerous stuff like nuclear applications when you want to run nuclear samples or irradiating samples. Therefore, we already manufactured systems like you can see on the scheme, where the sample part and also this furnace lift was placed in a hood. So you could load your sample in a safe hood, either for irradiation or for toxic purpose or corrosive purposes. You were able to operate that with gloves or with a robot in the hood. The system is closed, and the measurement technique, which is physically uncoupled from the sample chamber, from the hot chamber, is mounted on top of the glove box. And therefore, even that tricky applications are possible easily, considerable easily with such a setup, just to mention that. And finally, on the last slides, as said, this is a short webinar because I'm only introducing this one technique. I have some applications and typical measurements that are done with that kind of instrument. The first one that I can show you, I want to show you, is the isothermal absorption of carbon dioxide by a zeolite. A zeolite is a special ceramic sample. It is porous. It has micropores that usually trend to absorb a lot of gases, a lot of molecules. And typically what's done in the absorption setup, the magnetic suspension balance is used to monitor the weight. And then you increase the pressure from low pressure to high pressure. So on this graph, you see a blue curve, which is the pressure that was increased from vacuum level to ambient or double ambient pressure, so 2 bars, stepwise. And by increasing the pressure stepwise, you can see a response on the delta M signal, so the mass increases a bit. There is a little drift on the very beginning, which is, sometimes you have effects like that if you operate in vacuum. However, it's still a considerable small drift over time. And then you can see the mass increase steps quite properly. With a classical thermal balance, you would have a huge influence when you change the pressure, because the balance unit is also seeing the same pressure, and therefore you have an artificial signal that you have to somehow calibrate. In the magnetic suspension balance, you can directly operate under pressure, and this mass increase you see is not because of the pressure causing the signal to be changed. No, this mass increase is real mass increase because the sample mass changes. Why? Because it's absorbing this reactive gas, in that case, carbon dioxide. And out of studies like this, you can do absorption kinetics, you can do diagrams, pressure depending, temperature depending, how much sample or how much gas sample can be absorbed under certain conditions by different samples by different materials, which is something typical a magnetic suspension balance is designed for. Another application that's done on both systems, as well as classical one, as well as the magnetic suspension balance, is so-called coal gasification. The typical coal gasification experiment means you have carbon-containing biomass, you have carbon-containing samples that, as said, can be biomass, it can be charcoal, it can be anything like that. And this test, this so-called coal gasification, is an experiment where you access the bound carbon by water steam, you transform it into carbon monoxide, and from there you go further to methane gas, to methanol, to other alcohols, to usable molecules, usable gases, by adding in water vapor under a certain temperature and pressure. So what you do is you heat up your system to a temperature maybe 300, 400 centigrades, and during heating you lose a lot of volatile components. Usually it's done in inert gas at the very beginning. In that case, in that example, the complete setup was done under nitrogen gas. The sample was heated. The red curve shows the mass loss. And after a certain time at target temperature, you start to add in water vapor. Once you do this, so this blue curve shows the water vapor flow. So it was activated over here. Once you start adding in the water vapor, the sample mass suddenly starts to sink down or to decrease rapidly, because of the coal reacts with the water vapor according to the equation. Carbon plus water gets carbon monoxide plus hydrogen, and any further it forms methane gas plus water again, and so on. And doing so, and the different temperatures, different pressures. So this example was done at 50 bars. Doing this in different temperature and pressure ranges, you can get an idea how good or bad your carbon is accessible and how you could use your bio waste, your biomass, and whatever your plant waste, and how reusable it is. That's very interesting regarding green energy. It's interesting regarding access to biomolecules or organic molecules that are made out of plants. It's also more or less green energy technique, and it's also a question of how to get rid of wastes out of plant waste, out of biomass from farms and so on. And that's, as said, a very frequently asked application for the standard thermobalance as well as for the magnetic suspension balance. And then I have to tell you that we have sometimes when we do new instrument research or when we do prototyping, we are working with partners from universities, from research centers. And we had a partnership with the INC in Leipzig, which was established a couple of years ago to improve or to further improve our magnetic suspension balance, to even add in this possibility to do evaporation, to do this plug flow application. And what they did research on iron oxide pellets that were used to get rid of hydrogen sulfides out of different technical processes. And the main thing that was done is you have these brown pellets you can see in the pictures. They are made mainly out of iron oxide, and they are used to get rid of hydrogen sulfide out of process gas by just bringing them into the gas stream. And then the hydrogen sulfide will react with the surface. It forms the iron sulfide and some water, and then you can regenerate it by bringing in some oxygen. The oxygen reacts again back with the iron sulfide. It releases some sulfur and forms iron oxide again, and it releases even more water and so on. And therefore you could get rid of hydrogen, the toxic hydrogen sulfide, and transform it into solid sulfur that you could even reuse, that is then gathered at the surface of these pellets. The effectiveness, the effect can be monitored by the magnetic suspension balance quite easily. And the idea was to fill these pellets in as a sample. Then they were dried with argon, and then they were brought to a certain temperature, and then this hydrogen sulfide was added as a gas. It is a very toxic, very corrosive gas. That's the reason why you need a magnetic suspension balance, because the classical thermal balance will just immediately corrode if you use that. And during this loading reaction, you could see there is a huge mass increase of these pellets because they take up the sulfur and form iron sulfide. Then you have a regeneration step. There you're bringing some oxygen. The reaction goes backwards. The iron is regenerated. Sulfur is collected at the surface. And then you can do another loading cycle. You regenerated more loading cycles. The purpose of this experiment is to check how many cycles you could use these pellets. So you could monitor the loading and unloading by oxygen regeneration for multiple cycles. And then, as you can see, from cycle to cycle, there's more sulfur gathered at the surface of these pellets. And therefore, the loading and unloading gets even smaller from cycle to cycle. And this graphic shows finally that about 7 to 8 cycles is useful. And then if you go to 9 and 10, there's almost no reaction anymore. And therefore, you have to regenerate or to waste your pellets after 10 cycles. And out of this data, you can try to optimize the structure of these pellets. You get them more porous, you give them more surface. Maybe you get rid of the sulfur in some way. And this is why such experiments are done, because it helps to optimize this process. And then, as said, the INC Leipzig, who did these experiments with us together, they also helped us to develop, or they developed together with us, this so-called plug flow application reactor. On these pictures here, you see in the chamber, you directly see the sample holding basket. So this is the hanging wire where the sample is hanging at. And then you see this part here on the left picture without sample. On the right picture, there's this sample crucible with this brown powder or brown pellet. And this part where it stands on is, you can be seen on the right side. So this is the so-called sample container with the plug flow setup. There's a meshed bottom, and this meshed bottom is then more or less passed by the complete sound gas. This needs to be done in the following way. You put this complete basket at the bottom of the chamber. In the bottom of the chamber, you see in the left picture, there's a little hole where the gas comes out. So the magnet lowers completely the floating part. It stands on this little hole, and the gas passes the complete container. Then you lift it, you bring it into weighing position, you determine the weight, then you lower it again, you again switch on the gas, there's some gas applied, you bring it up again, you measure the weight change. And doing this stepwise, standing it there, so put it there, float it with gas, lift it up, measure the weight, put it back to the bottom, float it with gas, and so on. These cycles can be done very fast, very precisely using the magnetic suspension balance. And this results in a graph like you can see on the left side. So you have cycles. The blue cycles are the H2S gas flow cycles. So you put it on the bottom, you activate the gas flow, you disable the gas flow, you lift it and get a weight information. Then you lift it again, you put it down again, you increase the gas flow, you lower the gas flow, you lift it, and so on. Out of these cycles, you get data points each time you lift up the complete thing, and each time you lift it up, you get values for your weight change. Out of that, you get this dark purple or dark red weight increase curve that gives you an idea how much gas is absorbed. And finally, after a certain time, you find a kind of plateau, and you could go into the regeneration phase. And this is how a plug flow reaction would be done or performed. And this kind of setup is absolutely impossible in a classical thermal balance, because there, of course, you could place your balance on the way that's always flowing through it. However, in the classical balance, you would have a lot of influence on your weighing signal and a lot of disturbance as well. And that's a clear advantage where the magnetic suspension balance can be operated in a way that the classical balance can't be. So far, about the applications, as said, I promised to be around about 30 minutes. It's a little bit longer than that now, but anyways, thank you for your attention at that point. I think it should be clear what the magnetic suspension balance is, how it's been operated, what it does. I showed you some examples, what we did and what we do with it. And at that point, I want to thank you for participation. Thank you for your time. There will be a short discussion. Some people might ask questions. If you want to ask questions, please now type them into the chat. Ask me, we will discuss them. For those guys who do not want to stay for that discussion part, thanks for joining. Thank you for participating. In case you have interest in that kind of product, or you have questions regarding the applications, or you have questions or are unsure if your application is possible with that kind of instrument, please feel free to write us a mail, drop us a mail, contact us by social media, or get in touch with us anyway. We will discuss this with you. Maybe we can find a solution for your application. Maybe we do another webinar and go into detail. We are open for that, so don't hesitate to contact us if you need any more information. As said, for those who want to leave us, thank you for joining. I hope you enjoy your evening. And yeah, the rest of the week, it's almost weekend now, only one day to go. So all the others, thank you for staying here. And if somebody has questions, please be so kind, let me know. I will stay for a couple of minutes to wait for questions and try to answer them as fast as possible. Yes, and just give me a second. I will just read through this, and then let's see if any questions are open or popping up here.